Delta S is always greater than or equal to 0. Forgive me for this formula. It's the only one in the video. This is the formula for the arrow of time describing entropy. It's the only formula in fundamental physics that distinguishes between the past and the future. The only formula that tells us about the flow of time. The entire world is hidden in it. This inequality is known as the second law of thermodynamics. It means that heat can only flow from a hot body to a cold one, never the other way around. It was discovered by a romantic with a tragic fate, Ludwig Boltzmann. This Austrian scientist was the first to understand what was hidden in this formula. He thus pushed us towards answering a question related to a huge anomaly. You can observe this anomaly just by looking out the window. Ludwig Boltzmann believed that our world consists of tiny atoms. He knew he was on the right path. He showed that the behavior of gases can be well explained by the collective movement of molecules or atoms. This discovery provided him with indirect evidence of the existence of atoms, but it didn't offer any way to observe them directly. The lack of direct evidence made Ludwig vulnerable to criticism from his colleagues. But this wasn't what troubled him the most. For decades, he tried to explain the origin of physical order. All his attempts, despite being scientifically fruitful, were unsuccessful. Ludwig's theory predicted that order should not grow, but disappear. This explained why a hot body cools down, why coffee dissolves in water, and why bird songs fade away in the wind. Ludwig showed that the microstructures of the universe destroy order, turning it into chaos. The increase in order around him worried Ludwig. He knew that something was missing in his theory, but he couldn't pinpoint what exactly. In 1906, exhausted from his attempts to solve this anomaly, Boltzmann hanged himself. From that moment, his body, composed of atoms, began to steadily and relentlessly decay, just as his theory predicted. The 20th century confirmed Boltzmann's correctness regarding atoms and partially justified his passion for interdisciplinary questions. Quantum mechanics, molecular biology, biochemistry, and the theory of evolution helped unify various scientific disciplines. But aside from these connections, there was another concept that linked all areas of knowledge: the idea of information. It was this that fascinated and eluded Boltzmann. The 20th century saw not only an increase in the amount of information, but also attempts by scientists to understand this phenomenon. This time, however, they were inspired not by the beauty of nature, but by the horrors of war. The need for secret communication during World War II led to the study of information using mathematical methods. Encoding and decoding messages became a major mathematical challenge. Pioneers in this field, such as Claude Shannon, Warren Weaver, Alan Turing, and Norbert Wiener, became known as the first cyberneticians. In the 1950s and 60s, the idea of information took science by storm. Information was neither microscopic nor macroscopic. It could be recorded on clay tablets or densely packed in a DNA chain. The independence of information from scale made it appealing to scientists from various fields. Biologists studied the coding of hereditary information in genes. Engineers invented communication devices. Computer scientists, psychologists, and linguists modeled the brain using electronic thinking machines. Despite its growing popularity, the physical nature of information, which worried Boltzmann, began to be forgotten. The word information started to be associated with the immaterial and the digital, but information has a physical nature, like atoms or the energy of their motion. It's not a solid or a liquid. It has no special particles, but it possesses a physical nature, like motion and temperature. Information is physical order. In 1949, Claude Shannon and Warren Weaver published the book The Mathematical Theory of Communication, where they described the mathematics of what we now call information theory. To properly understand information theory, they needed to separate the word information from its everyday meaning, that is, from some kind of significance. The desire to separate information from meaning had both technical and philosophical reasons. Technically, Shannon wanted to create machines capable of transmitting information regardless of the meaning of the message. Philosophically, the authors understood that information and meaning are fundamentally different concepts. People can give meaning to information, but what is transferred over wires is just information. For example, The phrase September 11 may evoke different associations in Americans and Chileans. Meaning is given by people. The integrity of perception doesn't mean that meaning and information are the same. To create a machine that transmits information regardless of meaning, Shannon needed a formula to estimate the minimum number of symbols required to encode a message. He was able to determine the amount of information needed to transmit a message and eventually derived the basic formula for the most efficient encoding of a message. This formula turned out to be identical to the entropy formula proposed by Boltzmann almost 50 years earlier. And this coincidence was not accidental. It indicates the physical nature of information and points to the fundamental connection between information and entropy. This physical nature of information, confirmed by the coincidence of Shannon's and Boltzmann's formulas, plays a key role in understanding how the study of atoms can help us understand humanity's technical progress. In this video, inspired by César Hidalgo's book, Why Information Grows: The Evolution of Order from Atoms to Economies, we will understand the mechanisms that contribute to the growth of information at all levels, from atoms to civilization. We will consider the history of the universe from the perspective of the arrow of complexity, not the arrow of time, because it is the growth of information that determines the history of the universe and its inhabitants. After the Big Bang, the universe moves towards disorder, along the path of increasing entropy. But at the same time, places of physical order concentration are formed in it. For example, the planet Earth. Over billions of years, the amount of information on Earth continues to grow, turning our planet into an oasis. Information and knowledge increase here thanks to the energy of the sun and the self-reinforcing mechanisms of the evolution of life. Everything that fascinates me, Ludwig Boltzmann and I think you, represents physical order or information. It is a high concentration of complexity that we observe every time we open our eyes, and it exists not because information is widespread throughout the universe, but because we are born of it and we ourselves generate it. In this video, you will get an answer to Boltzmann's question. You will understand the reason for the anomaly, why the increase in entropy in the universe goes hand in hand with the boundless growth of information. We will understand how the increase in disorder and chaos is combined with the growth of complexity and order, demonstrated by life. I'm Sasha, and this is Homo Deus. You probably don't remember this, but a few decades ago, you traveled through time. You were born, and during your birth, you traveled 100,000 years from the ancient world of your mother's womb to the modern technological society. When you were in the womb, everything around you was the same as what surrounded babies 100,000 years ago. But on the day you were born, everything changed. Being born in the 20th, and especially the 21st century, is an alien experience for most children. The modern world is very different from the one in which our species evolved. Our world is filled with objects, cars, lamps, clothes, and technology that once existed only in someone's imagination. However, what makes the modern world is not the materiality of objects, but the way matter is organized, that is, physical order, which represents information. The fact that objects are embodiments of information and imagination may seem obvious, but information is a fundamental aspect of nature, older than life itself. As life developed, the accumulation of information accelerated. For example, through the replication of DNA and RNA molecules. Living organisms are well-organized structures that process and produce information. However, what sets humans apart is the ability to encode large amounts of information outside their bodies, not only in books, records, and files, but also in artifacts and objects, from arrows and stone axes to quantum computers and the internet. Our ability to create objects that we imagine in our minds distinguishes us from other species, which are limited to what nature creates. Take, for example, one of the most expensive cars in the world, the Bugatti Veyron. It cost about $2.5 million. Evaluating the cost per kilogram of this car, about $1,300, we can compare it to the cost per kilogram of gold and silver. The cost per kilogram of a regular car ranges from $10 to $60. Thus, the cost of the Bugatti Veyron exceeds the cost of its weight equivalent in silver and the cost of the Hyundai Accent matches the cost of its weight equivalent in bronze. While comparing the kilogram weight of a Bugatti and a kilogram of silver may seem pointless, it says a lot about how physical order or information can be packed into a product. Imagine you won the lottery and received a Bugatti Veyron as a prize.
Not bad, not bad.
On the very first day, you accidentally crash into a wall. Your health is fine, but the car is beyond repair. What happened to its value? The dollar value of the car vanished in an instant, while the car's weight remained the same. This happened not because the atoms that made up the car were destroyed, but because the crash changed the order of their arrangement. When the parts that made up the car were disassembled and deformed, the information embodied in the Bugatti was largely destroyed. In other words, the $2.5 million value was not in the car's atoms, but in how those atoms were ordered. This organization of atoms represents information. Claude Shannon, the father of information theory, defined this information as a measure of the minimum amount of data needed to transmit a message. That is, the number of bits required to convey data about the organization of something. For example, the order of atoms that make up a Bugatti car. To better understand Shannon's definition of information, let's start with something simpler. For example, a tweet of 140 characters. A tweet, like a Bugatti, represents a small packet of information and is created for communication. However, from Shannon's perspective, the purpose of the tweet doesn't matter. Information is the minimum amount of data needed to transmit any message, regardless of its content. To represent the content of a tweet quantitatively, imagine a hypothetical game where you need to guess your friend's tweet using only yes or no questions. You have a book with all possible tweets. The game begins when your friend randomly selects a tweet from the book, and you must guess it by asking yes or no questions. Shannon teaches that the amount of information contained in a tweet equals the minimum number of such questions needed to guess the tweet with 100% accuracy. But how many questions is that? For simplicity, let's assume that tweets are written using an alphabet of 32 characters, and you have a table where each character has its ordinal number. The best way for you to guess your friend's tweet is to use each question to divide the search space of possible tweets in half, guessing the message character by character. So the first question should be, is the number corresponding to the first character greater than 16? If the answer is no, then the first character of the tweet is between A and P. The second question, is the number corresponding to the first character greater than 8? If the answer is yes, then the first character is between I and P. And so on. Each question halves the number of possible characters. With 32 possible characters, it will take 5 questions to guess each character. Therefore, a tweet of 140 characters will require 700 yes-no questions, or in the language of information theory, 700 bits. Shannon's theory is the foundation of modern communication systems. By quantifying the number of bits needed to encode messages, Shannon helped to develop digital communication technologies. He called his measure entropy on the advice of John van Neumann. The formula for this measure was the same as the formula for entropy in statistical physics, derived by Boltzmann almost 50 years earlier. However, Shannon's and Boltzmann's interpretations of the concepts of entropy and information are difficult to reconcile. For example, according to Shannon, if you randomly mix all the bits on your computer's hard drive, this will increase the amount of information. Such an action will erase all your photos, documents, and files. To convey a message about the state of a disk with random data, more bits are needed. A disk with photos and documents requires fewer bits because they contain patterns and correlations that can be compressed. Boltzmann's entropy is not a measure of disorder, but a multitude of equivalent states. Take your wardrobe as an example. Boltzmann's entropy is the number of ways things can be arranged on the shelves. Usually, there are more disorganized ways than organized ones. But if you suddenly get a second identical wardrobe, the entropy increases because things can now be arranged in even more ways. However, the mess in them doesn't increase. Thus, in Shannon's language, the concepts of information and entropy are functionally equivalent. Since the number of bits needed to create a message, Shannon's information, is a function of the number of possible messages that can be transmitted, the set of states we understand as entropy. But this doesn't make entropy and information the same. As Nobel laureate in chemistry Manfred Eigen noted, entropy pertains to the average physical state, while information pertains to a specific physical state. Let's return to the Bugatti. Our example with the car is more complex than with the tweet because it involves a specific arrangement of a vast number of atoms, not just 140 characters. We are not looking for any possible configuration of atoms, but one that corresponds to a Bugatti car. For example, rearranging the tires changes the arrangement of the atoms, but not the key properties of the car. Therefore, a Bugatti with rearranged tires is considered the same. The group of Bugattis in working condition is relatively small. The group of broken Bugattis includes more states and higher entropy, but carries less information, although it takes more bits to convey a message about them. But the largest group of possible variants is Bugattis in the form of iron ore and other chemical elements. Completely disassembling a Bugatti into its constituent elements destroys information, while creating a Bugatti embodies it. This example shows us that configurations of matter that embody information are rare and hard to achieve. The problem is that systems cannot freely transition from one state to another. The existing order of matter limits the possible transformation options, and moving from disorder to order requires many sequential steps. The paths from disorder to order are much fewer than vice versa. Therefore, if you shake a box of clock parts, it will take billions of years for the clock to assemble itself. A Rubik's Cube can easily demonstrate the relationship between available options and entropy, as you will never be able to solve it randomly. Out of 43 quadrillion possible states, only one is perfectly ordered. The cube can always be solved in 20 or fewer moves, but finding the right sequence of moves is not easy. The main solving method usually requires more than 50 steps. Thus, only a few paths lead to perfect order, and they are rare among the vast number of chaotic options. Similarly, in the universe, information that is, ordered states, are very rare. A similar orderliness can be seen in living nature. For example, in DNA molecules, the sequence of DNA nucleotides is not random. If you compare the actual gene to any animal with a random set of nucleotides, you can immediately see that there is a certain order, a meaning in the gene. Such meaningful information DNA sequences could not have arisen by chance. This is the result of billions of years of evolution and natural selection. From the multitude of random variants, nature selected, preserved, and refined the rare sequences that gave organisms an advantage. Just as it is difficult for a child to solve a Rubik's Cube, it is challenging for nature to create ordered DNA sequences that carry information. The definition of entropy based on the multiplicity of states is related to the ability to process information and perform computations. Therefore, it is related to intelligence. I think you know the game where a child needs to place objects in corresponding holes. At 14 months, most children cope with balls and cylinders, but struggle with cubes and polyhedrons. Placing a ball is easy because it looks the same at any angle. With a cylinder, it's not difficult either, as it doesn't change when rotated around its axis. But a cube can only be turned a few ways, and a polyhedron even fewer. A triangle with unequal sides, which has only one correct position, is equivalent to a Rubik's Cube for a child. By playing, children learn to find these rare states of low entropy. Finding rare but useful states is a simplified model of intelligence. All this is intuitively clear. So let's think about this. Where does information come from, and why is time irreversible? Together, these questions seem like a mystery. After all, time flows from order to disorder, yet the complexity of our world is growing. Does this mean the growth of entropy in the universe contradicts the growth of information? The irreversibility of time is the mechanism that creates order out of chaos. Ilya Prigozhin. Almost everyone has moments when they wish they could turn back time, but time only flows in one direction, from the past to the present, from youth to old age, from life to death. The irreversibility of time is an obvious physical reality that has long remained a mystery. Even Newton's and Einstein's theories of motion technically allowed for the reversibility of time and did not explain why a broken car doesn't reassemble itself. The irreversibility of time is interesting, not only as a natural mystery, but also because its connection to the physical origins of information. Both of these properties of the universe depend on the laws governing the behavior of large collections of particles. Together, the irreversibility of time, and the ubiquity of information create an even greater mystery. Irreversibility is associated with the universe moving from order to disorder. But on our planet, the opposite happens. We see that the amount of information is steadily increasing. This was clearly realized by 19th century physicists. Although looking out the window, they could see an accelerating and complicating world. They understood Boltzmann's discovery. The sound produced by a guitar fades away. The waves created by a stone thrown into a pond disappear when the pond returns to its calm state. This loss of information was explained by the physical laws discovered in the 19th century. However, the increase in the amount of information remained unexplained. Attention to this paradox increased when two Charleses, Charles Lyell and Charles Darwin, stated that the age of our planet is not 6,000 years, as the Bible says, but billions of years. This new impressive fact suggested that the anomalous increase in information observed by everyone had been going on for billions of years. But anomalies cannot be eternal. Therefore, the only logical conclusion is that something is missing in our understanding of nature. Ludwig Boltzmann's main success was his 1878 work, where he showed that systems with a large number of particles tend to states with minimal information. This is the second law of thermodynamics. The entropy of closed physical systems always tends to increase. Here's a simple example. What happens if you drop paint into a glass of water? The initial state, when you drop the paint into the water, contains a lot of information. There are only a few ways the paint can be in one place, and many ways it can be evenly distributed. The universe is full of examples where information and complexity increase. But where does all this information come from? According to the theories of Boltzmann, Maxwell, Gibbs, and Einstein, the universe should turn into a homogeneous soup without information and free energy. In the 20th century, it was possible to reconcile the understanding of the arrow of time and the physical origin of information. New theory showed that information is not an anomaly, but an expected phenomenon. A key thinker in this area was Ilya Prigogine, who received the 1977 Nobel Prize in Chemistry for his contributions to non-equilibrium thermodynamics, particularly the theory of dissipative structures. He proposed the idea that information naturally arises in stable states of non-equilibrium physical systems. This sounds a bit cumbersome, so to make it clearer, we need to understand the idea of a stable state and the difference between two stable states, dynamic and static. Here's an example of a static stable state. A ball thrown into a glass. We all know what happens. Shortly after the throw, the ball finds a stable position at the bottom of the glass. More interesting is an example with a box filled with gas. If we pump gas into it and wait a bit, the amount of gas on the right side of the box will equal the amount on the left side. However, the stable state of the gas is not analogous to the ball resting at the bottom of the glass. In the box filled with gas, all the molecules are constantly moving. A stable state is reached when the number of molecules moving from left to right equals the number of molecules moving from right to left. Therefore, the box with gas is more analogous to the example of a drop of paint in water. Now let's consider the stable state of a non-equilibrium system. A classic example is a vortex when draining water from a bathtub. It remains stable as long as there is water in the system and is information-rich because vortices are rare configurations of water molecules that do not spontaneously occur in still water. In a vortex, molecules move not randomly, but have a speed and trajectory correlating with neighboring molecules. The swirls of cigarette smoke, the movement of a campfire flame, the glow of a computer screen. Even you and your smartphone are examples of non-equilibrium physical systems. Prigogine realized that Boltzmann's theory is not applicable to what is observed on Earth, because our planet is a non-equilibrium pocket within a universe striving for equilibrium. Earth has never been close to equilibrium. The energy of the sun and nuclear decay in the Earth's core drive our planet out of equilibrium, providing the energy for the emergence of information. Earth is a small vortex of information, in the vast cosmos. Prigozhin realized that to understand the information-rich nature of the universe, one needs to understand the properties of non-equilibrium systems. He realized that they differ from the properties of Boltzmann systems with many particles. Prigozhin derived mathematical laws and principles governing the behavior of non-equilibrium systems, and he showed that on the other side of chaos lies information. For example, if you decide to slightly heat water in a pot, it won't organize itself into an information-rich state. But if you heat the water for a long time, it will become turbulent, and this chaotic movement already contains information. After chaos, the system comes to a highly organized state full of correlations and information. Let's take a closer look at the boiling water in a pot. Initially, the water heats evenly. This is an equilibrium state. But if you continue heating it, at some point, ordered structures appear, beautiful patterns and circulations where the water moves in a specific direction. This is an example of self-organization in a non-equilibrium system, as Ilya Prigozhin described. It turns out that in systems far from equilibrium, and most natural systems are such, order and organization arise by themselves. This is why the emergence of ordered structures carrying information on a non-equilibrium planet like Earth is not an anomaly, but a regularity. But every order has an enemy, entropy. It always strives to destroy ordered structures. As soon as you turn off the heat under the pot, these beautiful cells disappear without a trace. Similarly, in nature, entropy is always ready to consume islands of order as soon as conditions become slightly less favorable. However, information has ways to preserve itself. An excellent way is to reproduce, that is, to spread copies of its genes. I discussed this in detail in the video, What is Life? Another way was discovered by Prigozhin himself. He proved that non-equilibrium systems naturally come to a stable state where entropy production is minimal. Roughly speaking, the system itself chooses a development path where it has to spend as little energy as possible to maintain order. This makes it easier for information to survive. Just as a liquid takes the shape of cells when boiling, a non-equilibrium system strives for stable states. In these states, the emerging order will be maximally stable. In a sense, the system behaves like an intelligent being, choosing the optimal self-preservation strategy. This reveals the deep connection between entropy, information, and the potential emergence of intelligence during the evolution of the universe. Here, those interested may delve into the subtleties of non-equilibrium statistical physics, but our goal in this video is to understand the origin of information. Ilya Prigozhin and Grigor Nicholas noted in their brilliant 1971 work on the connections between non-equilibrium systems and life. Generally speaking, the destruction of structures is a situation that prevails near the state of thermodynamic equilibrium. On the contrary, the emergence of structures can take place with specific linear kinetic laws beyond the stability domain of states characterized by ordinary thermodynamic behavior. Simply put, in nature, when everything is in equilibrium, things usually break down and disappear. But when equilibrium is disturbed and various processes occur, new interesting structures and forms can arise that did not exist before. Imagine the improvisation of a jazz band. When the musicians play enthusiastically, new melodies and harmonies are born. But this music lives only for a moment and disappears if not recorded. Similarly, in physical systems, while in a state of improvisation, far from equilibrium, they create new structures and patterns, but quickly lose them due to their variability. Analyzing such systems can help us understand the origin of information on a fundamental level. For information to persist for a long time, be stable, and be able to evolve, additional stabilizing factors are needed. This is important for the emergence of life, intelligence, and culture. Edwin Schrödinger, Nobel laureate in physics in 1933, noted in his book, What is Life? That we cannot understand the durability of physically embodied information by looking only at liquid systems. Cigarette smoke, vortices, paint drops, and gases, all these are liquid systems. Imagine you're laying out a beautiful pattern from colorful pebbles on the beach. If the tide comes in, the waves will quickly destroy the picture. But if you could instantly glue all the pebbles together, turning them into a solid panel, The pattern would be preserved for a long time. It could be moved to any location. Something similar happens with information in nature. When information is embodied in something solid, structured, and stable, it can be preserved and transmitted much longer than in something fluid and changeable. This is why Erwin Schrödinger argued that solids are key to understanding life. Protein and DNA molecules, which contain all the information about living organisms, are aperiodic crystals. These structures do not repeat, but contain large-scale correlations. It is the crystalline structure that makes them ideal carriers of information. Thus, combining the ideas of Prigogine and Schrödinger, we can understand where information comes from, the stable state of non-equilibrium systems, and why it is preserved, because it is stored in solids. The poetic whimsy of such a combination is that according to it, our universe is both frozen and dynamic. However, the growth of information volumes implies something more than crystalline solids and dynamic vortices. For information to truly accumulate, the universe requires one more trick. This is the ability of matter to process information, that is, the ability of matter to perform computations. Imagine a tree. Essentially, it is a computer powered by solar energy. The tree responds to the length of the day and changes its behavior depending on the season, shedding and growing leaves, directing roots toward water, protecting itself from pests, etc. The tree constantly processes information from the environment using complex molecules, proteins. Of course, the tree has no consciousness and advanced language like ours, but it can process information in its own way. This happens because the tree is a stable structure formed in a non-equilibrium system. But trees are living organisms. Therefore, we cannot claim that the ability to process information, compute, appeared before life. For this, we need to consider simpler systems. For example, chemical reactions. Imagine a set of chemical reactions that turn some substances into others through intermediate compounds. If such a system constantly receives initial substances, it will first come to an equilibrium where the intermediate compounds form and break down at the same rate. But if you increase the flow of initial substances, equilibrium will be disturbed and the system will transition to one of several new stable states. It turns out the system chooses between them. And if you further increase the flow, new stable states, even more complex and ordered, will emerge. For example, chemical clocks may appear, compounds that periodically transform into each other. So if we can direct the system into different stable states by changing the concentration of initial substances, it will compute, generating different products depending on the initial data. This already resembles a primitive metabolism or even a cell changing its type. It turns out that complex chemical systems can process information. This means that the ability to compute, like information itself, appeared before life. Life became possible because of matter's ability to compute. By the way, there is a separate video on this important ability of matter on the channel. Boltzmann could not understand why order in the universe increases rather than decreases, as the second law of thermodynamics predicts. But life and intelligence can accumulate information and create order locally while accelerating the overall increase in entropy in the universe. As Erwin Schrödinger wrote in his book, life feeds on negative entropy, extracting it from the environment and discarding positive entropy. Thus, the paradox is resolved. Life and intelligence accumulate information at the cost of even greater entropy growth around them. Now, how is this all related to the irreversibility of time with which we started our discussion? Imagine a lake where about 100,000 biodegradable balls were dropped on the surface. Initially, the balls were all gathered in trucks, but then they were released into the water and they filled the entire surface of the lake. The question is, can we reverse the movement of the balls at any moment as if time flowed backwards? Could we return them to their original position? Let's imagine we have two fantastic machines. The first can instantly change the speed of any number of balls on our command, but it does this with precision limited by our instructions' accuracy. The second machine can measure the position and speed of each ball with ultra-high but still finite precision. Now let's try to use these two machines to reverse time. First, we set the speeds of the balls with low precision, say to 2 decimal places. Will it work? No. A system with thousands of balls that do not lose energy is a chaotic system. Even tiny inaccuracies in the initial conditions will accumulate very quickly. The accuracy of 2 decimal places is not enough to return the balls to their exact original positions. What if we increase the accuracy? Let's say 100 decimal places. It still won't work. As long as the accuracy is finite, time cannot be reversed. In a chaotic system, any inaccuracy will accumulate. It turns out to reverse time, infinite precision, infinite information volume is needed. This means that statistical systems cannot return to their initial state because from any present moment, there are an infinite number of paths back to it. Moving forward, such systems seem to forget their way back. This infinity, which Prigogine calls the entropy barrier, determines the irreversibility of time quite differently than in Newton's and Einstein's theories. For Prigogine, the past is not only inaccessible, it simply does not exist. The past is gone, although it was. In our universe, there is neither past nor future, only the present, which is computed at any given moment. The depth of this instantaneous nature of reality helps us unite statistical physics with computation. Prigogine's instantaneous universe suggests that the past is inaccessible because it is not computable at the micro level. Prigogine's entropy barrier forbids the present from evolving into the past, except in idealized systems like a pendulum or planetary orbits, which look the same moving forward and backward. Now is the time to understand another physical aspect of information, the one closest to people, the information we create with our knowledge and skills. Let's consider the products of our civilization from the perspective of the information embodied in them and the non-obvious properties that follow from this. Life is a constant information processing. We are always moving and doing something, driving cars, walking in the park, simulating virtual worlds, flying on airplanes, or salivating at the sight of fried spiders. The world is vast and constantly changing, and we try to keep up with it. Essentially, each of us is a small mobile neuron in a large socioeconomic system. We try to adapt and find a balance between our desires and social life. It's not easy. That's how life goes. We move, process information, and increase its volume with our actions in society. We create social structures to compensate for our limitations, and these structures also learn to process information. This way, we generate information in objects and words. For our society to accumulate information, there must be an influx of energy, physical preservation of information in solid objects, and, of course, our collective ability to compute. The energy for the growth of information on Earth comes from the sun. Plants receive it and turn it into sugar, then into oil. But we humans have learned to preserve information for a long time. We preserve it in objects, from the first stone axes to the latest telescopes and communication satellites. Creating them requires not only energy, but also our distributed ability to compute. Let's compare 2 types of apples: the ordinary ones that grow on trees and are sold in stores, and the apples from Apple Inc. in Silicon Valley. Both types are products embodying information, whether in biological cells or silicon chips. The main difference is not in the number of details or the complexity of the functions. Edible apples are created by tens of thousands of genes and participate in complex biochemical processes. The main difference is that ordinary apples appeared in the world and then in our minds, while Apple products like the iPhone or Vision Pro first appeared in someone's imagination and then became a reality. Ordinary apples are packets of information, while apples are also fruits of our intellect. César Hidalgo poetically calls them crystals of imagination. When we talk about products as crystals of imagination, we mean that they embody not only information, but also fantasy. This information generated in our minds and then realized by creating an object similar to what we imagined. Edible apples existed before we came up with their name, price, and market. They were already part of the world and were simply imported into our consciousness as an idea. But the iPhone and iPad were exported from our minds to the world because they first appeared in the mind and then became reality. So the main difference between apples and Apple products is not that they both embody physical order, but where this order came from. Imagination as a source is the fundamental feature of the information created and accumulated by humans. Think of physicist Stephen Hawking. At the end of his life, due to a severe illness, he was completely paralyzed and could not speak. But thanks to a special device that captured the movements of his cheek, he could communicate with the world. A computer voiced entire lectures and scientific papers for him. This is an example of a modern crystal of imagination, enabling communication with voice and movement. Another example is brain-computer interfaces like Neuralink, which is currently widely discussed. Imagine that soon you could control a computer with the power of thought, type, draw, play without moving a single muscle. Moreover, in his book The Fabric of Reality, physicist David Deutsch predicted that such interfaces in the future would allow us to create any virtual realities. These ideas started as imagination, fantasies, but gradually took physical form and became real devices. The imagination of scientists and engineers crystallizes in these technologies, giving humanity entirely new, almost magical possibilities. In the end, the economy is a collective system through which people accumulate information. If you think about how products expand our capabilities, you can look at wealth in a new way. It is the ability to package knowledge into physical objects that allows us to live much more comfortably than if we were left to ourselves. It turns out that wealth is directly related to humanity's ability to expand its capabilities. Markets make us richer not with money, but with wisdom. They give us access to the knowledge and imagination of other people accumulated throughout history. For example, physicist Michael Faraday, who lived in the 19th century, discovered the laws of electromagnetic induction, without which modern electric generators are impossible. He also invented the first electric motor, later improved by Tesla. So every time we dry our hair with a hairdryer, vacuum, or make a smoothie in a blender, we are helped by Michael Faraday himself, although we have never seen him, nor did our parents, or even grandparents. Thus, the economy is a system that transmits to us the knowledge and skills of Faraday, Tesla, Edison, and many other geniuses of the past. We can say that in every electrical device live the ghosts of these great scientists. So the world of things around us is not just dead objects, but a repository of the knowledge, imagination, and skills of other people. And of course, the ability to embody knowledge in objects is not unique to humans. For example, ants can also record information in the environment using pheromones. An individual ant is not very smart, but the colony as a whole can solve very complex tasks, building labyrinthine tunnels, regulating ventilation in them, finding optimal routes. Humans do the same thing, only not with smells, but by creating physical objects, from screwdrivers to pyramids. It is this ability to embody fantasies in the world of things that allowed us to create a society and economy much more complex than an ant colony. But what is our potential? Where can the path of technological progress and the growth of knowledge lead us? Physicist Max Tegmark, in his book Life 3.0, expresses his thoughts about the potential of life. In my view, the most inspiring of all scientific discoveries is that we chronically underestimate the future potential of life. There's no need to limit our aspirations and dreams to the 100-year span of life amid disease, poverty, and ignorance. Instead, thanks to technological advances, life has the potential to flourish for billions of years. And not just here in the solar system, but across the cosmos, which is far more interesting and vast than our ancestors could have imagined. This is amazing news for a biological species that can accumulate information and push the boundaries of its existence for centuries ahead. The Olympic Games are remarkable because they push the limits of human physical abilities. Science expands the boundaries of our knowledge and understanding of the world. Art opens new horizons in creating beauty and enriches our life experience. If the known boundaries of life can be extended by technology, what are its true limits? How much of the universe can be suitable for life? How much matter can life use to its advantage? How much energy and information can it extract? And how many computations can it perform? These ultimate limits should be defined not by guesses and logic, but by the laws of physics. Strangely enough, it's easier to understand the distant future of life than the near future from this perspective. If we compress the entire 13.8 billion year history of the universe into 1 week, the last 10,000 years of our history would occupy less than half a second. If future life strives to push boundaries as much as ours does now, it will create technologies and crystals of imagination to reach these final limits. But do we know for sure that future life will be so ambitious? No, we don't. It might become complacent and lazy. But there are reasons to believe that the drive for development is a kind of genetic trait of advanced life forms. Whatever life tries to achieve, intelligence, longevity, knowledge, or thrills, it will need resources. Therefore, it will have to develop technologies to limit and explore the universe's spaces. One can assume that life arises independently in many places in the cosmos. Then unambitious civilizations will remain cosmically insignificant, and the most attractive part of the cosmos will be occupied by the most ambitious life forms. Natural selection will work on a cosmic scale. Sooner or later, all remaining life forms will strive for development. Let's look at what can be done with the resources of our solar system and what resources we can obtain through space exploration. For highly developed life, the most important resource is baryonic matter, that is, everything made up of atoms and their particles. With the right technology, you can create anything from it: power plants, computers, or even living organisms. So let's figure out the limitations on energy sources and computing power for advanced life forms. Any discussion about the future of life inevitably touches on one or several concepts named after theoretical physicist and professor Freeman Dyson. Besides his bold visionary ideas, Dyson, along with Julian Schwinger and Richard Feynman, is the creator of quantum electrodynamics and other rigorous scientific theories. He believed that if a cosmic civilization aims to achieve great things, it will need to harness the maximum energy available from its solar system. When speaking about energy, he mocked humanity's short-sightedness. All the current energy needs could be met by collecting solar light from just 0.5% of the Sahara Desert's area. But why limit ourselves to the energy the sun sends to Earth? Why not collect all the solar energy? In 1960, Dyson proposed the idea now known as the Dyson sphere. The idea is to use the material from Jupiter to build a biosphere around the sun. Our descendants could enjoy 100 billion times more biomass and 1 trillion times more energy than we have now. Dyson thought that this was a natural step for any advanced civilization, to place itself in an artificial biosphere around its star. Living on the inner side of the Dyson sphere, you could always see the sun directly overhead, with its light coming from everywhere, reflecting off the entire surface of the sphere. To see the stars, you would have to rise to the sphere's outer side. A relatively simple way to create a partial Dyson sphere is to place rings of inhabited sections in orbit around the sun. For a full sphere, many rings at different distances and planes are needed to avoid collisions. You could also build a monolithic stationary sphere, where the sun's gravitational pull is balanced by its light pressure. Such a sphere can be built gradually, adding new statite satellites. They must be very light, about 100 times lighter than paper. But this is possible because a graphene sheet is thousands of times thinner than paper, while maintaining incredible strength. If the sphere reflects light rather than absorbing it, the light inside will be very intense. This will inflate the sphere from within, allowing it to support more mass. For a heavier solid Dyson sphere, you would need super strong materials capable of withstanding loads thousands of times greater than the foundations of skyscrapers. The sphere must be movable and intelligent to change its position and shape, letting asteroids and comets pass through special openings. For present-day humans, living on a Dyson sphere would be, to put it mildly, unusual or even impossible. There would be almost no gravity in orbit, and on a stationary sphere, gravity would be 10,000 times weaker than that on Earth. There would be no magnetic field to protect against solar radiation unless it's created artificially. But there's good news. On a Dyson sphere in Earth's orbit, we could have 500 million times more space than we do now. If we want to live in space in Earth-like conditions, there's another good news. Building such stations is much simpler than a Dyson sphere. Physicist Gerald K. O'Neill came up with the concept of cylindrical stations with artificial gravity, protection from cosmic radiation, a 24-hour day-night cycle, Earth-like atmosphere, and ecosystem.
Not bad, not bad.
These stations can orbit within a Dyson sphere or attach to its outer side. The idea is to take two enormous cylinders and make them rotate in opposite directions. Inside them, centrifugal force would create artificial gravity, similar to Earth's. The main thing is to keep the cylinder axes pointed at the sun. Special mirrors can be used to direct sunlight inside, so day and night can alternate like on Earth. Every 24 hours, smaller cylinders around the station can be used for agriculture. Although in theory, Dyson spheres are very efficient by our standards, they don't violate the laws of physics. Albert Einstein showed that when mass is converted to energy at 100% efficiency, even a small mass gives enormous energy, according to the formula E equals mc squared. Oops, the second formula in the video. If we had a lot of antimatter, which we don't have at all, we could easily build a power plant with 100% efficiency. Simply adding a teaspoon of antimatter to a tank of water would release as much energy as the explosion of 200,000 tons of TNT or a massive hydrogen bomb. This would last for about 7 minutes for the entire planet. But alas, all our current ways of obtaining energy are terribly inefficient. Digesting food, we use only 1/trillionth of its energy. If our stomachs were 1,000% efficient, one lunch would last a lifetime. Coal and gasoline are only slightly more efficient. Modern nuclear reactors extract 3 to 5% of uranium's energy. Even the fusion reactor of the sun, 10 times better than what we have, uses only 0.7% of hydrogen's energy. An ideal fusion reactor could theoretically reach 30 to 40% efficiency. But even that is far from perfect. We need something better. Stephen Hawking, in his book A Brief History of Time, proposed black holes as a source of energy. Previously, astrophysicists thought nothing could escape from them, not even light. But Hawking proved that due to quantum effects, black holes emit radiation, and the smaller they are, the stronger the radiation. Any substance falling into a black hole will eventually be emitted as heat, almost with 100% efficiency. But there's a problem. Until a black hole becomes the size of an atom or smaller, the radiation will be very weak, like from a candle. To speed up the process, we need holes 1,000 times smaller than a proton and weighing as much as a cruise liner. But even then, to force protons to fall into such a tiny hole, you need a powerful accelerator like a Large Hadron Collider, and part of the energy will be lost during the evaporation of the hole. It turns out that we'll spend more than we gain, meaning negative efficiency. Therefore, we need a quantum theory of gravity which we don't have yet to understand what can be done here. Fortunately, there are other ways to extract energy from black holes without quantum gravity. Many black holes spin very fast, almost at the speed of light, and this rotational energy can be extracted. A spinning black hole has what's called an ergosphere. It will be immediately captured and hurled around the hole. But if you throw the object at the right angle and break it in two beforehand, one fragment will fall into the black hole and the other will fly out with more energy than the object initially had. This way, we can siphon off part of the black hole's rotational energy. Repeating this process, you can drain all the rotational energy up to 27% of the black hole's mass if it spins at maximum speed. The giant black hole at the center of our galaxy weighs 4 million times more than our Sun. Even 10% of its mass would give as much energy as converting the mass of 400,000 suns into energy with 100% efficiency, or as much as 500 million Dyson spheres around suns for 1 billion years. Yes, I can't wrap my head around these numbers either. There are more ways to get energy from black holes without quantum gravity. For example, if you can extract energy from matter falling into a black hole, nature already does this in quasars. A quasar is a kind of cosmic power plant that converts the gravitational energy of matter falling into a black hole into powerful radiation visible from great distances. That's why they are called the beacons of the universe. Gas spirals closer to the black hole, forming something like a giant pizza. The inner part of the pizza gradually gets sucked into the hole, and the gas heats up and glows brightly. Gas particles accelerate, their energy grows, and the movement becomes chaotic. As a result, the gas heats up to enormous temperatures and starts radiating intensely. If you build a Dyson sphere around such a black hole, you can collect this radiation and use it. The faster the black hole spins, the better. Efficiency up to 42% for the fastest black holes. There's another known way to convert matter into energy without black holes. It's called the Sphaleron process. Imagine you have a construction set with two types of pieces, red and blue. The red pieces are quarks, tiny particles that make up everything around us. The blue pieces are leptons, another type of particle. There's a special rule. If you arrange red pieces correctly, they suddenly turn into blue ones. In the real world, this is called the Sphaleron process. Quarks can turn into leptons, but for this to happen, they must come together in a specific way and pass through an intermediate stage called the Sphaleron. The most interesting part is that when quarks turn into leptons, the leptons weigh less than the original quarks. Where did the rest of the mass go? It turned into pure energy, just like in Einstein's famous formula. So the Sphaleron process is a kind of trick to turn matter, quarks, into energy without any black holes or complicated quantum physics. Future intelligent life may be able to build a Sphaleronizer, an energy generator akin to a powerful diesel engine. A regular diesel engine compresses a mixture of air and fuel until it ignites, pushing a piston. The combustion products weigh slightly less than the initial mixture, and the mass difference turns into thermal energy. A Sphaleronizer would compress ordinary matter into monstrous temperatures in the quadrillions of degrees, then let it expand and cool. Our early universe already conducted such an experiment 13.8 billion years ago, when it was just as hot. Although all the matter turned into energy, leaving less than 1/billionth of a fraction as quarks and electrons, each then formed atoms. A Sphaleronizer would be 1 billion times more efficient than a diesel engine, and anything with quarks would suffice as fuel. Due to this high-temperature process, the early universe produced 1 trillion times more radiation, photons and neutrinos, than matter, quarks and electrons, which later formed atoms. Over 13.8 billion years since the Big Bang, a great segregation occurred. Atoms gathered into galaxies, stars, and planets, while most photons remained between galaxies as the cosmic microwave background. In the future, advanced life will be able to convert almost all the matter in galaxies into energy. This will restore the tiny proportion that existed in the early universe and briefly recreate the hot and dense state inside the Sphaleronizer. To understand the efficiency of a Sphaleronizer, we need to clarify some details. For example, its size must prevent significant loss of neutrinos and photons during compression. We don't know this yet, but one thing is clear: the energy prospects are far better than our current technologies allow. For our lunch's physical efficiency is 10 billion times worse than the limits set by the laws of nature. What can we say about our computers? Their efficiency, as we see now, is even lower than food. Professor Seth Lloyd of MIT, a pioneer in quantum computing, believes that our entire universe is a quantum computer. He showed that computation speed is limited by energy. According to his calculations, a 1 kilogram computer, at best, perform 5 times 10 to the 50th power operations per second, which is 36 orders of magnitude more than a modern laptop. We'll reach this in a few centuries if performance continues to double every 2 years as it has been. Also, according to Lloyd, a 1 kilogram computer can store a maximum of 10 to the 31st power bits, 1 billion times more than a modern laptop. Seth acknowledges that even superintelligent life will find it hard to reach this limit. The memory of such an ultimate 1 kilogram computer would be like a hydrogen bomb explosion or a piece of the Big Bang, but he optimistically believes that practical limits are not far from physical constraints. Already, quantum prototypes have achieved storage at 1 bit per atom, which, when scaled, gives 10 to the 25th power bits per kilogram, 1 trillion times more than an ordinary laptop. And if electromagnetic radiation is used for communication between atoms, speeds will increase to 5 times 10 to the 40th power operations per second, 31 orders of magnitude higher than my computer's processor. Now we see clearly the computational prospects of future life are dizzying. The ultimate 1 kilogram computer surpasses today's supercomputer as much as it surpasses a blinking car turn signal that stores 1 bit and switches 1 a second. From a physics perspective, everything future life can create, from habitable zones and machines to new forms of life, is just specially ordered elementary particles, crystals of imagination. Just as a whale has rearranged krill cells, and krills are rearranged plankton cells, so are our solar system is hydrogen, rearranged over billions of years of cosmic evolution. Gravity gathers hydrogen into stars, where it forms heavy atoms. Then gravity shapes them into planets, where chemistry and biology create living matter. Future life, having reached technological limits, can rearrange particles much faster and more efficiently. First, though, powerful computations. It will find optimal methods, and then it will implement them using available energy sources. We have seen how matter can be turned into a computer and energy, so that's the only necessary fundamental resource. When future life hits physical limits, it will have only one way to grow: expand into the cosmos, deep into the universe. Compared to cosmic timescales of billions of years, the intellectual explosion lasts a moment during which technologies plateau, limited only by the laws of physics. This technological plateau is significantly higher than any of today's technologies. If we continue to improve our technologies with sufficient caution, anticipating the consequences of possible mistakes to avoid them, Earth life has immense potential to flourish both on Earth and far beyond for billions of years, something even the boldest of our ancestors could not dream of.